Today we're going to learn about the properties of logarithms. When I say learn, I really mean review, because you did learn these things back in Algebra 2. Properties of logarithms, and these are the properties that allow us to expand and condense logarithms. You might remember those terminologies. But we're talking about the product rule, the quotient rule, and the power rule of logarithms. And they go like this. If there is a multiplication, a product, in the argument of the logarithm, this can be written as the sum of two different logarithms that have the same base. Using the same kind of logic, if there is a quotient, fraction, inside the argument of a logarithm, this can be written as the difference of two logarithms with the same base. It's always going to be top minus bottom if you're doing that way. It's always top minus bottom. And the last logarithm property is if you have an exponent in the argument of a logarithm, that exponent can be moved to the front of the logarithm as a coefficient. Now, of course, anything in math that can be done can be undone, so all these rules can be used backwards and forwards. So if ever you see the addition of two logarithms that have the same base, you can combine that into a single logarithm that has a product in the argument. If ever you see the difference of two logarithms, you combine that to be one logarithm that has a quotient in the argument. And if you have a number sitting on the front of a logarithm, you can move that to the exponent position of the argument. So all of our rules work backwards and forwards. So let's practice using these rules. This one says, proving that this thing is actually something that you're allowed to do. So when you prove something to be true, you're not ever allowed to use the assumption that it's true. You'd have to start with the thing on the left. Okay? And this property can be proven pretty easy, to be honest with you. Now, in the past, I haven't bothered showing this to the students because they didn't care, and I'm not going to make you reproduce it. So I guess my question becomes, is this something you want me to demonstrate? Show you why it's true? Okay. So here's what we're going to do. Let's assume that log base b of m times n has some kind of value, an unknown value. What we can do is we can cancel log base b using exponential base b, like this. So now we have some base raised to the x is equal to a product of things, like that. Well, or did I start this one backwards already? Trying to remember if I did this backwards already or not. No, I can't remember. It's been a long time since I did this. I just showed this to my IB students just the other day. Trying to remember how I proved this. It uses that trick that I said that any number can be written as a base of something else. I'm just trying to remember how to pull this off. Well, let me think on it. I'll come back to it. While I'm teaching the other stuff, I'll think on it. I can't remember what the trick is. There is a trick to it. It uses log base b of b, or b raised to the log base b of b. But let me think on it for a little bit, okay? Until then, let's keep going. I'll come back to it. We'll finish the notes there. This says to expand this logarithm into as many logs as possible. Basically, a logarithm is not fully expanded until you have a single thing in the argument, okay? So if ever you have more than one object in the argument, and that includes exponents, you are not fully expanded. So the first thing we're going to do is we're going to see that we have products here. And all of those products can be written as sums of different logarithms. They have the same base, though. These are the common log. They all have base 10. So we say log of 8 plus log of x plus log of y to the fourth. But this is not fully expanded. because that last logarithm has two objects in its argument. So what we can do here is we can take our exponent using the exponent law and just bring it to the front. So we get a full expansion, log 8 plus log x plus 4 log of y. Easy peasy lemon squeezy? Okay. Well, this one's a little bit crazier. But it says, all right, go ahead and use the properties of logarithms to expand this. What I see is a fraction in my argument. So that means we can do the ln of, because this is a log, the ln of the first one, being the top, minus the ln of the denominator. However, again, you're not fully expanded until there is a single thing in the argument. I would like to point out, though, that the 3 rules I put at the top of the page, none of those rules dealt with a sum in the argument, and none of those rules dealt with a difference in the argument. And that's because there are no properties for that. So sums and differences in the argument, they can't be dealt with, unfortunately, so they're just stuck the way they are. But this is not finished, though. I'm sorry, McKinley?
What's the ln for?
That's the logarithm.
Oh, you're just writing it quicker. Oh, ln.
Well, just because it said to expand it. So it was handed to me as an ln, so I'm just using ln instead of common log. I actually could have used, well, no, I can't use change of base on this one.
Could you have used log though?
No, because log of x is not the same as log of, or ln of x. Because it was started as an ln, we needed to finish it as an ln of log base e.
Oh, I missed that part. I missed that. Sorry.
No, that's fine. Alrighty, the square root bar, that represents an exponent for us. That's the 1/2 power. So we're not finished until we bring that 1/2 to the front as a coefficient. And you need to make sure that you keep the argument in parentheses. Otherwise, it looks like ln of x squared. Oh, plus the number 5. And it doesn't work like that. It's the ln of quantity, x squared plus 5. Now this is fully expanded. I can't do anything with that first argument because of the sum that is inside it. I'm not allowed to move any exponents to the front because of the sum that is inside it. Because there's a summation there, I can't. I'm finished. That's it. It's stuck right there. There are no properties that deal with sums or differences in the arguments, unfortunately. It'd be nice if there was, but there's not.
Mr. McCutcheon.
Yes, sir.
If it would be a cube root, would it be 1/3 ln x cubed plus 5?
Yes, if it was a cube root, yeah, the cube root would have been the 1/3 power. Good? Those are good questions. Well, anything in math that can be done can be undone. That means if I can expand a logarithm, take it apart, I must be able to condense a logarithm, use the properties to put them back together. You may have noticed, okay. An announcement.
Interruption. We are going to have a shelter in place drill.
Oh, this is the shelter in place drill.
Please move away from windows and doors. Avoid auditoriums, gymnasiums, and other structures with large roof spans. This is the shelter in place drill.
Okay, so we are now sheltering in place while we learn. Great. Continuing. I don't know if you guys noticed, but on those 2 examples that we just did when we were expanding the logarithm, I moved the exponents last. Did you guys notice that? Well, if you're going to condense the logarithm, since this is like an inverse operation, if you want to think of it like that, it needs to happen in the reverse order. So if you have numbers sitting in front of your logarithms, they have to be moved to the exponent positions first. So this 2 belongs here first. So I have the ln of x to the 5th minus the ln of xy squared. Now I can deal with the fact that there is a subtraction sign between 2 logs that have the same base. These are both log base e. So since I have a subtraction of 2 logs with the same base, I can combine this to a single logarithm with a fraction in its argument. The first one is always the top, and the second one will always be the bottom. You could write this as x squared y squared if you want to, but there's really no reason to. If there's only what now? Be more. Okay, more announcements that were just canceled. Great. You were asking about an exponent. I'm sorry.
Yeah, if there's only
Oh my gosh.
Thank you for practicing safety. This ends our shelter-in-place drill. Have a wonderful day.
Awesome. Okay, great. Anyway, you were saying?
if there was an exponent only on the y, can you not bring it over?
Shh. If there's an exponent only on the y, you mean can I not put it in the front of the logarithm?
Yeah.
You have to deal with the product first before you move the exponent. So moving exponent should be the last property that you apply. And the reason why is because let's just say it said the ln of xy squared and only the y had the square. If you move that 2 first and then you split it, you're implying that both the x and the y had that exponent. So no, exponents need to be dealt with last when expanding, dealt with first when condensing. What I can do for this question is I could simplify it a little bit if we cared to. If we cared to simplify it, I mean, you could write it as the ln of x to the 5th over x squared y squared, like I said a moment ago. And the only reason why you would bother doing this is so that you could simplify the x to the 5th over x squared.
Are you gonna make it to the
I don't think so. I don't think that's something I required you to do on the test, but it's not like it's difficult. There. But it was fully condensed right here. That was just if you wanted to simplify the argument a little bit. So a moment ago, I actually mentioned another property of logarithms that we haven't learned, quote unquote, this year yet. I mean, you did learn it in Algebra 2 Honors. And I mentioned it, but we haven't talked about it yet. And that would be the change of base property. If you flip your notes over, that's where they begin. So the back side of the notes has the property called the change of base.
Oh, the calculator thing.
The change of base property says that you can take a logarithm of any unknown base and you can actually write it as a quotient of 2 logarithms as long as they have the same base. Now you can change the base to anything you want when you write this quotient. And that's why it's called the change of base formula. So I say log base b of x. I could call this log of x over log of b, ln of x over ln of b. Or I could go and do something really crazy like pick a random base and say log base a of x over log base a of b. So that's why it's called change of base. It is a very useful property when trying to solve crazy, ridiculous logarithm questions by hand. It's very useful. It's also the way that you are going to type or evaluate your logarithms on a scientific calculator. Now, your graphing calculators have the ability to do log base b. At least the newer versions of the graphing calculator do. I don't know about the older versions, but the newer version of the graphing calculator like mine, the log base function, it's actually called log base. It's in the math commands. So grab my graphing calculator. In case you ever wanted to do it at home, press the math key that's on the left.
Hey, Mr. McCutcheon, I remember this from last year. My calculator also has that function. It's just a regular one.
Which calculator is it?
It's the Casio.
Oh, the Casio Scientific? Yeah. So the reason why the Casio Scientific calculators can do that is because Casios are made for engineers, and engineers generally don't understand the math that they're doing. I'm kidding. They don't want to waste their time with math that could be done by technology when they're trying to fry bigger fish, So typically Casio calculators, they're geared towards engineers, and anybody that's going to be an engineer in college, the first thing they're going to make you do is get a Casio graphing calculator, not a TI graphing calculator. If you're not going to be an engineer, though, the TI graphing calculator is perfect. But yeah, so the Casio Scientific can do log base, but the TI Scientifics cannot, that I know of. So on the TI graphing calculator, you press math and scroll all the way down to the very bottom. It's almost at the very, very bottom. And it's just called log base. That's the command that it's called on the calculator. And like I said, on the TI Scientifics, Yeah, you're just going to have to use change of base. So if I said, what's log base 2 of 3? You would type log 3, close parentheses, divide by log 2, close parentheses, and you get your answer. So for these examples here, I'm actually going to pretend that I don't have a graphing calculator that can do this for me. Instead, I'm going to use change of base and then use a TI 30x2S or even that TI 30XA. The 30XA is a colossal pain in the butt because you have to type the argument first. But this is how we're going to deal with this. Log 16 divided by log 3. On the 30XA, you would have to do 16 log, then divide by 3 log, and then you would have to hit the enter key at the very end, otherwise your answer is not correct. If you're using the TI 30x2S, you could type log 16, close parentheses, divide by log 3, close parentheses, and then hit equals. Either way, you should get 2.523-ish. And by the way, I could have done ln 16 over ln 3, and I would have gotten the exact same answer. That doesn't mean that log 16 equals ln 16. It just means that the ratios, the proportion's the same. That's all that means. For some reason, this camera's cattywampus. There we go. Okay. This one, log 10 over log 6. Log 10 is special, though. It's 1 because that's the common log. The argument and the base have the same value. That's log base 10 of 10, which is just 1. So 1 divided by log 6. That one's even easier on your calculator. Should get about 1.285-ish. I forgot to use my squiggly equal sign. Forgive me. And
I'm
part
getting
C.
2.0959.
I'm sorry?
I'm getting 2.0959.
For which one?
This one.
You
Oh
did
wait,
one.
I'm doing log 3.
You mean the first one then?
No, I was accidentally mixing up the first and the second one. I was
Oh,
putting
okay. You were just mixing them up. I got
S.
you. So part C, the answer is -1. I don't need a calculator for that. But that's because 1/2 raised to the -1 power equals 2. But just to drive home the idea, if you didn't see that, you go, okay, log 2 divided by log of, and instead of using a fraction, I'm going to say 0.5, because that'll be easier to type. Either way, you're going to get the answer of -1. So even though it said use a calculator, you don't need to all the time. You're faster than a calculator if you know how to evaluate logarithms. If you can see that it works, you are faster than the calculator. At least you're faster than the person using the calculator because they have to spend time typing it. I love these last two questions. Absolutely love them. It says, describe how to transform the graph of ln of x into the graph of the given function. What that means is changing the base of a logarithm is actually a type of transformation. Isn't that cool? But Mr. M, I've never heard of this changing the base of the logarithm transformation. I thought transformation's never the same no matter what function. You're right, they don't. Transformations never change. What that means is I'm going to use properties of logarithms to show you that changing the base is a transformation that you know and trust already. This is so fun. For me, at least, because I'm a huge nerd. Okay. Part A. We have that g of x equals log base 5 of x. We're trying to figure out what transformation was done to the ln of x, which, by the way, is log base e of x. We're trying to figure out what transformation has been done to ln of x to create log base 5 of x.
The e was turned into a 5.
Well, it's not that you can't just say you changed the e into a 5. What you have to do is you have to use change of base and go, tell you what, instead of writing this as a log base 5 of x type of thing, why don't I write them both as ln of x using change of base? I'll call this the ln of x divided by the ln of 5. That's the same thing as saying 1 over the ln of 5 times the ln of x. And since ln of 5 is a number, 1 divided by ln of 5 is a number, you have simply multiplied your ln of x by some irrational number. So what we need to do is we need to figure out what 1 divided by ln of 5 is. It's about 0.62. And since 0.62 is between 0 and 1, this is a vertical shrink. So changing from ln of x into log base 5 of x is nothing but a vertical shrink. Vertical shrink factor, and I'm not going to say factor 0.62 because that's not exact. I'm going to say factor 1 over ln 5. So cool that changing the base can be manipulated into showing that it is a vertical stretch or shrink and or reflection as well. Because if it was negative, that also would have been a reflection. Neat, huh?
Why do you have to use ln instead of log?
Because the parent function that we're trying to transform is ln. That's the only reason why. Yeah, if the parent function had been log x, then I would have used log instead of ln.
Okay.
Part B. We have that h of x is log base 1/4 of x. Same trick. Use ln's. This is the ln of x over the ln of 1 over 4. Isn't 1 over 4 actually 4 to the negative 1 power? It is, right? Okay. So let's continue to use our properties and realize, oh, that argument has an exponent in it. I can move that exponent to the front of the logarithm, right? And, bless you, when you have a negative sign for a fraction, it could either be on the top or the bottom, or just written right in the middle. So I'm going to go ahead and write it as written right in the middle, because that's the way I like my fractions to look. Then lastly, to really see this as transformations, I'll just say this is negative 1 over the ln of 4 times the ln of x. So yeah, there are two transformations going on there. The negative sign is its own transformation, and the 1 over ln 4, which has a value of around 0.72, this is going to be equal to roughly negative 0.72 ln x. Two transformations. A reflection over the x-axis, and then a vertical shrink of factor 1 over ln 4. So cool.
Oh, go back up. Go
I
back
will.
up.
Calm yourself. It didn't go anywhere. Reflect over x-axis. I have people in the back that couldn't see. Then a vertical shrink. Of factor 1 over ln 4.
Is that how it's gonna show up on our test too?
I don't know. The point is you could do this. I don't think I have transformations of these things on your test. It was just interesting to see it done this way. All right, and the exciting conclusion of the proof. I finally remembered how to do it. Just took a little bit of brain power. Here's how we're going to do this. Let's try again. Let's let m equal, I don't know, log, that says bog. Let's try again. Let's let x equal, let's let x equal log base b of m. So I'm defining a new variable. If x equals log base b of m, this implies, transing it back into its exponential form, that m equals b to the x. That's just writing it back in exponential form. And let's, at the same time, let's let y equal log base b of n. Putting this in its exponential form implies that n equals b to the y. So if you look back to the original statement, log base b of mn, there's the product of mn in there. So log base b of mn, according to our substitutions, would be log base b of, now m is b to the x, and n is b to the y. But, you know, when you multiply two numbers with the same base, you add their exponents, right? So far, so good? But log base b cancels exponential base b. So this leaves us with x plus y. And if you go back to the original substitutions, x is log base b of m, and y is log base b of n. There it is. Yeah, that one's the hard one to prove because of that little trick that you had to do with substitutions. But there you go. Proving it without using any of the other properties. And once you have one property proven, it's very, very easy to prove the other three.
And the other ones